Hello everyone, and welcome back to our channel. In our first video, we successfully handled the installation of PostgreSQL and established a clear understanding of the database, schema, and table hierarchy. If you're new here or missed that installation step, I highly recommend you pause this video and check out the link in the description below before continuing. So let's get started.
Welcome to your channel, Invisible Tech Guru, unlocking tomorrow's tech today.
Today, we're diving into the absolute fundamentals of building robust data structures, PostgreSQL Data Types. It's a foundational topic, and I think many of you already have some experience here. But let's take a moment to catch up and solidify our understanding, because truly, choosing the right data type is the most crucial decision you'll make when creating a database. In this session, we're not just going to list names. We're going to learn the definition of each data type with an understandable purpose and practical usage. PostgreSQL offers a rich set of types, but we'll focus on the major categories that make up 90% of your database needs.
Every column in your table needs a data type. This tells PostgreSQL exactly what kind of information to store, which is crucial for data integrity. So at first, what are numeric data types? Numeric data types are essential tools in a database system, serving as the blueprint for storing any kind of quantifiable information, that is, numbers. Think of them as specialized containers. Some are small and fast for whole numbers, others are large and slow but guarantee perfect accuracy, and still others are fast but allow for tiny errors. The choice of which container to use depends entirely on the data you need to store and how you plan to use it. These numeric types are grouped into 4 main categories, each optimized for a specific goal: integers for whole numbers, arbitrary precision decimals, floating point numbers, and serial types for automatic counting. So let's begin our deep dive into the first and most fundamental category, integer types. It is one of the most commonly used data types in PostgreSQL. It stores whole numbers and requires 4 bytes of storage. It uses for storing the population of a country, tracking user counts on websites or social media platforms, or representing counts in inventory management. As you can clearly see in this diagram, the set of integers is broadly categorized into 2 main groups: the negative numbers, which are all the numbers less than 0, and the whole numbers, which start at 0 and include all the positive counting numbers. Furthermore, the whole numbers themselves can be broken down into 0 and the natural numbers, also commonly referred to as the positive integers, illustrating a clear hierarchy within the number system. Let's look at a real-world example of how to use the integer data type in PostgreSQL. Imagine we are building a database to track simple statistics for a national park, specifically the number of annual visitors and the number of trees planted in a given year. Both of these statistics must be whole, non-fractional numbers. We will create a table named ParkStats using the integer data type for both columns. First, we create the table, and then we insert some typical data. In this code, we use integer for annual visitors and trees planted. Since the count of visitors can easily exceed 32,737, the standard 4-byte integer is the appropriate medium-sized bucket to use, as it can hold values up to 2.1 billion. If we attempted to insert an entry like 2025, 300,000.5, 6,000, the database would immediately reject the row and issue an error because the annual visitors column cannot store the fractional component of 0.5. When we query the data back using select star from ParkStats, the output will be, as you can see, every piece of data in the annual visitors and trees planted columns is a clean, whole number, fulfilling the contract of the integer data type. Now that we have covered the fast and simple integer types, we need to address data that requires absolute precision, particularly for financial data. This leads us to our second category, arbitrary precision decimals. Arbitrary precision numbers are numbers whose size isn't limited by fixed computer data types like int or double, but rather by the available system memory, allowing for calculations with extremely large integers or precise decimals, crucial for cryptography, scientific computing, and avoiding overflow errors in tasks like calculating large factorials. Instead of fixed bits, they use dynamic storage, like arrays of digits and algorithms mimicking manual math, long division or multiplication to handle digits as needed, offering precision at the cost of speed compared to hardware arithmetic. The core reason to use this numeric data type is to prioritize data integrity over speed. Here are some key advantages of using it, like arbitrary precision numbers are essential because they prevent the loss of detail inherent in standard fixed-size data types, enabling perfect accuracy for financial systems and enormous scale for cryptography and advanced scientific calculations by dynamically expanding their storage, which avoids both rounding errors and limits on size, like overflow. Let's look at a real-world example of how to use the arbitrary precision numbers in PostgreSQL. Here, I am defining a table called staff pay, where the salary column uses numeric 6,2. This declaration is key, as it enforces that the salary must have a maximum of 6 total digits with exactly 2 digits reserved for cents, the scale. This means the number of dollars before the decimal can be no more than 4 digits, limiting the maximum salary to $9,999.99. First, we create our table, and next we attempt to insert 3 test values to demonstrate the 3 core rules of numeric: perfect fit, automatic rounding, and error rejection. And in output, we can see the query, the data for employees 1 and 2, and observe the result of the failed insert for employee 3 because the insertion failed. The salary of $10,000.00 requires 5 digits before the decimal, which exceeds the limit of 4 allowed by our numeric 6,2 declaration. I think this example helps you to understand the use of arbitrary precision numbers. Now we move on to the third category, which sacrifices this exactness for blazing fast performance: floating point types. A floating point data type is a fundamental computer format used to represent real numbers, that is, any number that includes a fractional or decimal part. Floating point numbers are modeled on scientific notation. Internally, they are stored using 2 main components: the mantissa, which holds the significant digits and defines the number's precision, and the exponent, which determines the magnitude and scale. This is why the decimal point has a dynamic position, allowing it to float around the number's digits. The 2 most common types are float, which is typically single precision, using 32 bits, and double, which is double precision, using 64 bits for much higher accuracy. The major advantage of floating point types is their unmatched range. They can represent the vast distance between galaxies and the tiny distance between subatomic particles, all within the same format. This is essential for most scientific, graphical, and real-world engineering calculations. However, this comes with a crucial caveat. They use finite precision. This means many simple numbers, like the decimal 0.1, cannot be stored exactly. They are held as an approximation. This is why comparing 2 floating point numbers for perfect equality might not work as expected. Therefore, you choose floating point when you need a wide range and fast computation, accepting a small margin of error for complex numbers. The CHAR data type in PostgreSQL is one of the essential character data types for storing fixed-length strings. Unlike VARCHAR, which stores variable-length data, CHAR is used when we need to store a fixed-length string. When we define a CHAR n column, n specifies the maximum number of characters the column can store. If the input string is shorter than the defined length, PostgreSQL will pad the string with spaces to match the specified length. However, any attempt to store a string longer than the specified length will result in an error unless the string is padded with spaces, which PostgreSQL will trim. The CHAR type is best used when we need data that follows a consistent length, or when we need to ensure fixed width formatting for specific data types, like country codes and currency symbols. Syntax: variable name char n. It specifies the fixed length of the character field. N must be a positive integer. If n is not specified, it defaults to 1. But if the length n is not mentioned, the default value is char 1, meaning it stores a single character. Let's take a look at some of the practical examples of using the char data type in PostgreSQL to better understand the concept and how this data type works. We will create a table with char data type. We write char check table with 2 columns. X is a fixed-length character column with a length of 1, and Y is a fixed-length character column with a length of 10. So here is the create script. Now, let's insert data into the char check table that exceeds the defined lengths of the X and Y columns using below command. So if we run it, then it shows error, that value too long for type character 10. To correct the errors and insert valid data, we can fix the string lengths. Here, we have inserted a string of exactly 10 characters into the Y column, including trailing spaces to meet the char 10 requirement. So if we write this insert query, now that we have managed to successfully assign the values to the character data type, check it by running the below command. Select * from char check. So I think you can understand the use of the char data type now. Let's look at the VARCHAR data type. In the world of relational databases, PostgreSQL stands out with its robust support for various data types, including the flexible VARCHAR data type. It is defined with a maximum length expressed as varchar n, where n represents the upper limit of the string length. If n is not specified, the varchar type behaves similarly to the text data type, allowing for strings of unlimited length. This syntax is variable name varchar n. One unique feature of varchar can be used without a length specifier. In this case, it behaves exactly like the text data type, allowing you to store strings of unlimited length. This is incredibly useful when you don't want to set an arbitrary limit on things like user comments or descriptions. Now, let's see the difference between the char and varchar. In PostgreSQL, unless you have a specific reason to use a fixed-length column, varchar is generally considered the standard best practice because it prevents the trailing space issues that often occur with char. So, in the next video, we are diving into the other major data types you'll need to know.
Thanks for turning in. Don't forget to like, subscribe, and hit the bell for more of the latest in technology. See you in the next update.